Hello. I'm starting the section on inequalities today. That's section 1.7. I will do 2 videos. This is a long section, so I'm going to do it in 2 videos. I'm doing the first video. So that's going to be the first part. And I will upload a second video after this one. Okay, so on inequalities, so we have been working with equations. In the first 6 sections, we have been working with equations. Now we're going to work with inequalities. Those are going to be the last 2 sections of chapter 1. So an inequality says that one expression is greater than or equal to, less than or equal to another. As with equations, a value of the variable for which the inequality is true is a solution of the inequality, and the set of all solutions of the inequality is the solution set of the inequalities. So 2 inequalities with the same solution set are equivalent. Okay, so the inequality symbols that we're going to be using. So the inequality symbols are less than, greater than, less than or equal to, or sometimes this reads at least, and greater than or equal to. Or sometimes it reads at most. So something like x less than or equal to 7. This reads all real numbers less than or equal to 7. Or -1 less than x less than or equal to 4. This reads all real numbers. All real numbers greater than -1 and less than or equal to 4. Okay, so on the number line, so I'm going to cut this to include a graph. Okay, so the first one on a number line. That's going to be all real numbers less than or equal to 7. So we are going to indicate with a bracket. So a bracket represents that the end value is included. So it's going to be 7 and anything less than 7. And the graph of -1 less than x less than or equal to 4 on a number line. So we indicate with a bracket the less than or equal part, we indicate that with a bracket, and with a parenthesis, we indicate that the n value is not part of the solution set. So that's going to be the graph on a number line. So the first one, x less than or equal to 7, that includes 7 as part of the solution set. And -1 less than x less than or equal to 4, that includes -1 as part of the solution set, but excludes 4. Okay, so to represent the solution set, we're going to use interval notation. So look at this example, the second example. So anything between -1 and 4, excluding -1 but including 4, can be a solution. Like 4 is a solution, 0 is a solution, but also 1/2 is a solution, or 0.2389 is a solution, and so on. Okay, so we will represent solution sets, or we will use interval notation to represent solution sets. So I'm going to copy this part. I'm going to copy interval notation. Okay, so I'm going to start. So I'm going to copy the first part. The first 3 intervals are open intervals. And we're going to be using the infinity symbol. So the symbol, this is not a number, this is just a symbol. The symbol infinity is the infinity symbol. Okay, so I start with the first 3 types of inequalities. These are on page 151. Infinity will always have a parenthesis. So every time we don't include the n values, and infinity is not a number, it's a symbol, every time we don't include the n values, we write parentheses. The first inequality, so the first 3 intervals are open intervals. In set notation, this reads, the first one reads x, such that x is greater than a. On interval notation, that's going to be a comma infinity. Both have parentheses, and we have the graph. Everything to the right of a, excluding a. The second interval is going to be a comma b within parentheses, which means that, so in set vector notation, it's going to be the set of all x, such that x is greater than a and less than b, and we are excluding the n values. The third interval is going to be all x, or all real numbers that are less than b. So if we don't have a bound on the left, we're going to write minus infinity. So that's going to be everything to the right of, or everything to the left of b, excluding b itself. If we include the n value, we write a parenthesis. So these are the next three intervals. So the set of all x such that x is greater than or equal to a. Since a is part of the solution set, we're going to indicate that with a bracket. And again, infinity doesn't have, infinity always have a parenthesis. So it's going to be everything to the right of a, including a. The set of all x greater than a, less than or equal to b. That's written parenthesis a, comma b, bracket. The set of all x such that x is greater than or equal to a but less than b, that's going to be written bracket a, comma b, parenthesis. And the bracket indicates that the end value is included. The parenthesis indicates that the end value is excluded. And the set of all x such that x is less than or equal to b. The interval is written minus infinity, comma b, bracket. And the graph is going to be the set of, it's going to be everything to the left of b, including b. And the last three. When the interval has bounds at the left and the right, and the end values are included, that is called a closed interval. So the set of all x greater than or equal to a, less than or equal to b is going to be a comma b within brackets, within square brackets. On a graph is going to be the same. It's going to be all the values included. So all the values including a and b. At this joint interval is going to be the union. So this symbol represents union. So this symbol is union. When we solve inequalities, sometimes we're going to have two separate inequalities, and we write with the union symbol. We put the intervals together with the union symbol, like the set of all x, such that x is less than a or x is greater than b, where a is less than b, is going to be written like that. And you have two intervals, and those may have, I mean, they only wrote this with parentheses, but they may have brackets, like minus infinity a bracket, union parentheses b infinity, or some other combinations. And to indicate the set of all real numbers, we write minus infinity, comma infinity. So we're going to write solution sets in interval notation. The next properties are the properties of inequalities. Let's suppose that you have two real numbers or three real numbers, a, b, and c. So if a is less than b, then adding the same number to both sides of the inequality is not going to change the inequality. If a is less than b, and you multiply by something positive, then the inequality is preserved. And if a is less than b, and the inequality, and c is negative, then the inequality is reversed. So replacing less than with greater than, less than or equal to, or greater than or equal to, results in similar properties. Restrictions on C are the same. So in general, number one, if A is less than B, then adding the same thing to both sides will not change the inequality. And the same is true for any inequality symbol. That can be greater than, or less than or equal to, or greater than or equal to. In any case, the inequality is preserved. Number two, If A is less than B and C is positive, then the inequality is preserved. And this is still true for any other inequality symbol. So if it's greater than, the inequality is preserved, or less than or equal to, or greater than or equal to, the inequality is preserved. And number 3, if we multiply by something negative, the inequality is reversed. So if A is less than B, and C is negative, then A times C is greater than B times C. And the same is true if we reverse the inequality. I mean, the same is true for other inequalities. If we have greater than, the inequality flips or reverses. Yeah. And it's going to be the same if we subtract or if we divide. So with divisions, it's going to be the same thing. Like we can even do A over C is less than B over C when C is positive. And if C is negative, A over B less than B implies that A over C is greater than B over C. So we are going to be solving linear inequalities. So I will cover linear inequalities today, and I'm going to start quadratic inequalities. A linear inequality in one variable is an inequality that can be written in the form ax plus b greater than 0, where a and b are real numbers and a does not equal 0. And we only write this with greater than 0, but we can use any of the other 3 symbols. We can use less than, or less than or equal to, or greater than or equal to. Okay, so we're going to use the properties to solve linear inequalities. We are going to solve the linear inequality. And write the solution set in interval notation. Okay, the inequality is 4x minus 13 is greater than x plus 8. So just like we did with the equations, we are going to isolate on one side, isolate x on one side. So the first property works exactly the same as it does with inequalities. We can add 13 to both sides. So 4x is greater than x. A plus 13 is 21. And we can subtract x from both sides. So 3x is greater than 21. if we divide the inequality by something positive, the inequality is preserved, and we have that x is greater than 7. So that's not the solution yet. That's still an inequality. The solution set is going to be, so everything greater than 7 is going to be 7 to infinity. We have a greater than. If we have greater than or less than, we write a parenthesis to indicate that the n value is not part of the set. So the solution set is 7 to infinity. So this was example 1. Example 2. We are going to solve the inequality 2x minus 12 greater than or equal to 6x minus 14. So we're going to isolate x on one side of the inequality. So we can add a 12 to both sides. 6x, then minus 14 plus 12 is going to be negative 2, or 6x minus 2. And next, subtract 6x from both sides. And the opposite of 4x is greater than or equal to negative 2. So you need to be careful whenever you divide by negative 4, because we're dividing by something negative, and the inequality symbol will reverse. So we cross that, indicating that the inequality symbol will reverse. So minus 4x over negative 4 is x. We divide it by something negative, and the inequality symbol reverse, and negative 2 over negative 4 is 1/2. And the solution set is going to be everything to the left of 1/2, including 1/2. So the solution set is negative infinity, 1/2 bracket. So remember, infinity and negative infinity will always have a parenthesis next to them. So I'm going to do an application. Example 3. This is on page 152. If the revenue and cost of a certain product are given by the revenue is 4x and the cost is 2x plus 1,000, where x is the number of units produced and sold, at what production level does R at least equal C? So they are asking us at least equal, so they are asking us when does the revenue is greater than or equal to the cost. So the idea is to make a profit, or the idea is that the revenue is greater than the cost, or the worst case scenario, to break even. But R is 4x. So we're going to solve for x greater than or equal to 2x plus 1000. So let's subtract 2x from both sides. And 2x is greater than or equal to 1000. Subtract, or not subtract, divide both sides by 2. And x is greater than or equal to 500. The solution set is going to be 500 to infinity, including 500. So if at least 500 units are produced, and sold, R at least equals C. The revenue at least equals the cost. And the value of 100, the value of 500 is known as the break-even point. Okay, so the last type of linear inequality I'm doing, and then I'm going to do quadratic inequalities, is going to be a three-part inequality. So we are going to solve the inequality -3 less than 2 minus 5x less than or equal to 13. And what we do, if you have this type of inequality, what you do is isolate x as the middle term. Okay, so we can start. So let's write this. Let's write the original inequality. If we isolate x as the middle term, we're going to first add or subtract 2 from all three parts. And -5 is less than minus 5x less than or equal to 11. And we're going to divide by -5. Divide all three parts by -5, but at the moment we divide by -5, we're dividing by something negative, so the inequality reverses. So -5 over -5 is 1. The inequality reversed. -5 over -5, that's what we did. And 11 over -5, the inequality reverses, is -11 over 5. Or if you want to read it from left to right, this is the same as -11 over 5 less than or equal to x less than 1. So the solution set, -11 over 5 has, -11 over 5 or x is greater than or equal to negative 11 over 5, we're going to write it, we're going to indicate that with a bracket. The solution set is bracket negative 11 over 5, and 1 is, or x is less than 1, so we have a parenthesis. And we're going to do quadratic inequality. So I'm going to do one example today, and I will continue next time. With quadratic inequalities, the approach is slightly different. So this is what a quadratic inequality looks like. A quadratic inequality is an inequality that can be written in the form ax squared plus bx plus c less than 0, and we can replace, I mean, the inequality symbol can be any of the four inequality symbols. It can be greater than, or less than or equal to, or greater than or equal to, where a, b, and c are real numbers, and a does not equal 0. So I'm going to copy also the steps to solve a quadratic inequality. Okay, the first step, we're going to solve the corresponding quadratic equation. Once we solve the corresponding quadratic equation, we're going to have the solutions of the quadratic equation will determine 3 test intervals. And we're going to pick a test value from each interval to determine which intervals form the solution set. Okay, so this is going to be the last example I'm doing today. I will continue next time. We are going to solve x squared plus 2x minus 15 less than 0. Okay, so step 1. We are going to solve first the associated quadratic equation. The associated quadratic equation is going to be x squared plus 2x minus 15 equals 0. Okay, so that is something that can be factored. We can solve this equation by factoring. The expression on the left factors as x plus 5 and x minus 3. So this has two solutions, negative 5 and 3. Okay, so this expression, the expression x squared plus 2x minus 15 becomes 0, is 0 only at negative 5 and 3. Anywhere else is going to be positive or negative, and it's not going to change from positive to negative without becoming 0 first. So let's draw a number line. Okay, so we know that this expression becomes 0 at -5 and 3. So at -5 and at 3, this becomes 0. And anywhere else, that's going to split the number line in 3 intervals, where the expression is either going to be always positive or always negative, but it's not going to change sign. It's not going to change from positive to negative or from negative to positive without becoming 0 first. So I probably need to yeah, so I'm trying to make this tablet to work. Okay, there it is. So there becomes 0. Okay, so the numbers 5 and 3 divide the real number line into 3 intervals. That's going to be step 2. The numbers -5 and 3 divide the real number line into 3 intervals. Those are -∞, -5. -5, 3. And 3 to infinity. And the expression x squared plus 2x minus 15. This is always positive or always negative inside these intervals. And at 0, it may change sign. So we need to test the values. So this is always positive. Or always negative in these intervals. Okay, step number 3. In step 3, we are going to make a table with the interval knowing that the expression is always positive or always negative inside these intervals. We're going to pick a test value. And whether is x squared plus 2x minus 15 less than 0, true or false. The first interval is -∞ to -5. Second one is -5, 3. And the third one is 3 to infinity. So we can pick any test value in each of these intervals, but we're going to take something that is easy to evaluate. Like from -infinity to -5, we could pick -10, or we could pick -25. But I'll try to keep it simple and pick -6. So let's plug it into the expression on the left. That is going to be 9. We know that 9 is negative, so this is false. So x squared plus 2x minus 15 less than 0 is false. Between -5 and 3, the easiest value I can think of is 0, the easiest to evaluate. So this is 0 squared plus 2 times 0 minus 15, which is going to be -15. So this is -15, which is negative, so that is true. And on 3 to infinity, we can pick 4. And evaluate. 4 squared is 16. 16 plus 8 is 24. 24 minus 15 is 9, which is false. And the solution set is -5,3. So these were our findings. I'm going to draw, or I'm going to go back to that number line. So we ended up finding that that the expression x squared plus 2x minus 15 is positive on -infinity, -5. It's negative on -5, 3, and it is positive on 3 to infinity. So the solution set is -5,3. So I'm going to stop the video here, and in the next video, I will do another example with quadratic inequalities and an application. So thank you for listening.